I call myself an experimental quantum biologist, and I'm not going to talk about consciousness, so I'm a transition speaker to the topic of the next theme starting tomorrow. So this is a preliminary talk. Thank you.
That's your forward effort.
Yep.
Man, this laser pointer.
Ooh, I got a real laser pointer.
Yeah,
Ooh, cool. And I'm not going to actually talk today about quantum biology or consciousness, but I'm going to talk more about quantum chemistry. I'm going to talk about some experiments I did a while back, quite similar to what Dean Radin talked about yesterday, but opposite. He talked about, well, I'm going to talk about the effects of a quantum system on a biological system, and he talked about the effects of biological systems on quantum systems. So in that sense, it's a kind of mirror image. So I'm going to start with the introduction. That was the introduction. Okay, now I can go forward, except slide's not going forward. Do I have to will it to go forward? Do I have to will it to go backwards? That one, right? Oh, see? It wasn't me. So in the way of the introduction, if you read the abstract, you will see some introductory comments, but in fact the real introduction to the talk, thank you, is based on not my idea, but a colleague of mine, Dr. Omura, who happens to be an MD in New York, who did these experiments with laser beams. He published it in his journal, which he's the editor, which he set up his journal so he could publish some of his unconventional ideas, where he's talking about molecular information and having biological effects. So what this guy does is he takes a drug and he puts it, you know, on his hand. He puts the laser beam, oh, I have a laser beam, over the top of the drug, and he points it at people. Now, who would ever think to do such a thing? Well, I thought that was a really cool experiment, and I wanted to do it in a more scientific method. So this is my experimental setup, shifted to the left, and I did an experiment, another experiment we have here with nerve cells. We heard about that earlier in this conference. But in this case, I'm shining a laser beam directly on the Petri dish containing the nerve cells, but here is a powder form of a drug, which is an MAO inhibitor. And there's no interaction between the beam and the chemical powder, so it's just over the top of, just like Dr. Omura did. And what I'm measuring in the nerve cells is the enzyme activity of monoamine oxidase. So here's the actual experimental protocol. Nerve cells, you split them in half, you get 6 control, 6 experimental. 3 treatments. One is the control unmodulated, one is the modulated laser, and one is the drug by itself. You harvest the cells, you measure the monoamine oxidase activity with a standard biochemical technique. You express the enzyme activity as picomoles per minute per milligram. I know there's at least one other biochemist in here would appreciate that. So here's the results. Here's the control. The laser by itself, no statistical significance. The drug, as expected, caused a large inhibition of the enzyme activity, but the laser with modulated information caused an increase in the enzyme activity at the p equals 0.01 level. So here's an anomaly. And the reason I never really published this data or even thought about it since I did this experiment 10 years ago was because there was really no explanation that I could find in the scientific literature to explain how this might occur. But nowadays, with the modern quantum chemistry and quantum physics, I think I have some sort of an explanation. So before I look at the explanation, let's look at the interpretation of what's happening, or what I think is what's happening. There's some kind of information from the chemical which is transferred to the laser. The laser then carries the information. The laser is modulated. The laser delivers the information to the biological system, and the enzyme decodes or demodulates the information and causes a biological effect. Okay, well, there's a lot of stuff going on here, and I really only have time, I'm sure you've heard that before, to talk about the first step. Let's talk about chemical information. What could possibly be coming from a chemical in a solid state in a powder form that might actually be picked up by the laser? Well, so let's first look at the chemical structure. This is the enzyme inhibitor. It turns out to be an antidepressant, MAO inhibitors. You've all heard of MAO inhibitors. And there are three particular chemical interactions that are going on here that I want to talk about. First is the hydrogen-hydrogen coupling. Then there's the hydrogen-oxygen coupling. And then there's the really interesting stuff that's going on inside the benzene ring itself. I can divide chemical information into four different categories. Charge, three-dimensional charge information, information from the chemical bonds that I just described, quantum information, and electronic information. And if I have time, I'll talk about all four of those. So looking at the distribution of charges on the molecule, because some of the nitrogen has got a positive charge, oxygen has a negative charge. So you do have an electrostatic field that's generated. So it turns out that in some of the more sophisticated molecular modeling programs that are out there, there is a particular one called comparative molecular field analysis, where they look at exactly that, the distribution of charges, and they measure the electrostatic potentials, and they calculate all these parameters about a particular molecule. Of particular interest to me is the map of the electric field distribution, which is of course used to correlate with the biological activity and the three-dimensional structure and structure-activity relationship. It turns out that drug companies actually use this kind of chemical analysis to predict what structures would actually have what effects. But the results of these kind of experiments, analysis, are shown with this particular molecule, which is different than the one I use, but it's got a benzene ring and it's got some carbons and a nitrogen. So here's the graphical data of the electric field emitted by such a molecule. Here's the benzene ring, and here's the rest of the molecule. So you can see that, okay, we have some kind of electrostatic field generated by the molecule which might couple with the laser. Okay, that's reasonable. Next, let's look at the chemical bond information. Well, if you all remember from Chemistry 101, in formation of a chemical bond, electrons are shared by both atoms, and you can measure the vibration of the bond, the stretching, the twisting, and you get what's typically called a fingerprint if you look in the infrared spectra. And this is kind of a typical infrared spectra for the people over there, and you've seen infrared spectra before. And each peak corresponds to a different kind of vibration or twisting mode. Froelich actually proposed, mathematically predicted that there would be longitudinal vibrations in addition to transverse vibrations. And more recently, they have gigahertz and even terahertz spectroscopy, which measures this kind of information in the very, very high frequency range of the spectrum. So you can get a lot of information about the chemical bond from this kind of spectroscopy. In addition to the classical way of analyzing a chemical bond, there is more recently the field of quantum chemistry and the fact that they predict that there's sort of information that can be obtained. These are the three kinds of bonds that we're going to talk about, and in fact the quantum processes associated with these bonds are either spin coupling, spin-spin coupling, superposition, or proton tunneling. So we can look at that in a little more detail, but let's first look at quantum chemistry, something I haven't heard talked about at this conference for a while. Ever, rather, sorry. So quantum chemistry is started back in the late 20s when Schrodinger and Dirac, of all people, said, hey, we've got these quantum field theories, let's see if we can apply it to a chemical. Let's see if we can develop a quantum theory of the chemical bond. And shortly after that, they were actually Linus Pauling, proposed that the electrical orbitals of a molecule can be considered a molecular wave function. And then, more recently, then algorithms were established for this wave function. And more recently, in modern quantum chemistry, we have an amazing number of theoretical approaches to analyze this kind of problem. The one that I particularly like is this one called the quantum theory of atoms and molecules. Well, what an original name. But QTAIM, I mean, that's in the, believe it, in the scientific literature. And then we've got the phenomena of bodons, which was mathematically described and analyzed, which are considered the quantum particles of a chemical bond. So indeed, this is the mathematical modeling. There's all kinds of experimental spectroscopic methods, which you probably haven't heard of. And then there's NMR, which we've all heard of, because NMR measures proton spin states. So, and they can measure it in a solid state. I'm working in a solid state. So if we look at some of the NMR type of data, we can see that proton-proton coupling occurs because the nuclear spin is quantized. It exists in two states, all the spins going up in one direction, all the spins going down. These two states can act as like a quantum bit, like a 0 and a 1 in the quantum information theory that we've talked about. And these protons are spin 1/2 systems. And in the NMR data and in the mathematical analysis of NMR data, they talk about spin 1/2 systems as being qubits to define a quantum system. And they talk about spin-spin coupling in molecules. So there is a rather strong scientific support for proton-proton coupling. Now, quantum resonances, I was talking about the benzene ring, very interesting molecule because actually Carl talked to us about enantiomers. Well, here's two structures which are mirror images of each other. The carbon bonds you see are on opposite sides of a mirror. These two structures could form the two qubits which make up a quantum system. Well, I could propose that to you, but in fact, ironically enough, in the chemistry literature, they talk about the fact that neither of these two structures exist, but what exists in the real world is a resonance hybrid structure, which is a superposition between both structures. And this is what is actually defined as a resonance interaction between the different carbon bonds, and electrons are delocalized and all this stuff. So benzene is a very interesting molecule, chemical structure to look at within my molecule here. Hydrogen bonds are the electrostatic bonds between oxygen and hydrogen, well known to stabilize the tertiary structure of proteins and DNA. And if anybody heard my talk several years ago about the conformational structures of DNA, it turns out that the hydrogen, the hydrogen bonds hold the DNA together. It turns out hydrogen bonds are very sensitive to external energies, including subtle energies. Oh, and energies of consciousness. I am talking about consciousness. There we go. I feel like I'm fitting right in. Okay, so the hydrogen bond has been described as a quantum process where delocalization of electrons occurs. There's cooperative effects, and there's proton tunneling, all described in the conventional scientific literature. Okay, so now we've looked at charge distribution, chemical bonds, quantum bonds. Now, electronic information, of course, is information about the electronic structure. And electrons can have some very unusual properties themselves. They can exhibit tunneling. They can exhibit coherent excitations. They can be delocalized. They can correlate. So electrons themselves can have quantum properties. So all of these different components of my chemical offer information which can be transferred to the laser beam. So I like to propose that even in a hologram, propose the existence of a quantum chemical hologram. Even in a chemical, I guess you could say this chemical has a consciousness. I'm even feeling more welcome at the moment, by the moment. So I'm going to propose the existence of a chemical hologram, which is defined as the synergistic interaction between all the energetic levels comprising the physical substance, which I've talked about all of these. I haven't talked about the subatomic. But the conclusion is that this quantum chemical hologram, which I should first mention, biological holograms were first proposed by Edgar Mitchell and Carl Pribram, to give credit where credit's due. But chemical holograms, I guess, that's me here. I don't think anybody's talked about that, but if anybody knows about that, I'd be happy to hear it. So, in conclusion, what we're saying is that the chemical hologram carries the information, transfers it it to the laser transfers it to a biological system, and that the biological system then responds and can have either the same effect as the original chemical, or in my case, the opposite effect. Now, as Carl was talking about earlier, maybe this opposite effect is because the enantiomer of the molecule is the opposite. It's like a left versus a right structure, that maybe only, the other half got transferred to the hologram. That information got transferred to the laser, transferred to the biological system, and that caused the opposite biological effect. But the conclusion is that this kind of a mechanism could very well occur between two people. It could occur via some form of a laser or light, or other kinds of energies between two people, so that the information, whether it's bioinformation or chemical information, could be transferred between two people and allow for the communication between two people. That's it. Thank you so much.
Thank you so much. Do we have some questions? Yes. Julie?
Tired audience. Everyone's falling asleep. Maybe not.
I wish all my chemistry professors would have been as dynamic as you, Glenn.
Oh, well, thank you.
If I can stop sneezing. This is very interesting. Do you think that this may be the mechanism behind, now I just forgot the word, homeopathy remedies, where there's no actual chemical in the remedy, and it often has the opposite effect of what the original chemical.
That's true. And what we don't understand is how to transfer the chemical information, whether it's from into water or into a laser beam,
Right.
how to really negotiate and control the conditions so that we get the opposite effect or not. But of course the application is that you don't have to deliver the drug to the person, you can deliver the information. Homeopathy is a great example, and obviously water is very different than a laser, but this is a parallel to the talk I gave 2 years ago about homeopathy and information in water.
I was not here at that time.
Oh, okay, there we go.
I'm just reminded of that joke about I want my martini so dry, I just want, is it vermouth? I just want the word vermouth whispered over the...
There we go.
It just carries the energy there.
Okay, here comes a hard question.
Oh, yeah, watch out.
From Chalmers himself.
No, this is not so much a question as a suggestion and speculation. This opposite effects business seems very puzzling on your informational model. Neurons don't declare opposites day, as far as we know. However, cells do normally exist in an electromagnetic environment as well as a chemical one, and cells also have regulatory mechanisms to maintain homeostasis for basically all of the chemicals that they produce and use. It seems to me a plausible explanation of the opposite effect is that your laser is conveying much less information than the full structure of the MAO inhibitor molecule. But what it is passing along might be the kind of information that natural internal radiation would pass along in a living body, which would signal neurons that, there's MAO inhibitor in the vicinity, we'd better stock up.
That's quite feasible. The purpose of the experiment was really just to see if I could affect specifically the enzyme, because remember there are 1,000 enzymes in these nerve cells, and the information was rather specific for this one particular molecule, and I measured the one particular enzyme, and in fact there was an effect. So the fact that there was an effect at all to me means like, yeah, there's a perturbation going on, and we just don't have the exact experimental conditions to figure out how to do it experimentally, let alone how it's done in the body because of the endogenous electromagnetic fields surrounding a cell. But yeah, this kind of information is probably passed on between two neurons, and as I said, in conclusion, between two people. So, good point. Thank you.
Hi, this is probably a very stupid question, but
No such thing.
because everybody's so tired, they won't remember this tomorrow anyway, so
I
I'm
will.
gonna go ahead. Trying to break down your possible pathways for the information carrying. So what type of information is being carried, whether it's quantum, electrochemical, electromagnetic, or whatnot. Would it make any sense for you to introduce a quantum interference, let's say a measurement/entanglement, into the quantum information of your test chemical, without actually trying to change the electromagnetic or electrochemical structure of your test chemical, and see whether that actually changes any of the test results or not?
Well, in fact, I didn't do that, but Dr. Omura did in his original experiments with his laser beam. When he was projecting chemical information onto a person, he discovered that if he put an aluminum foil, aluminum foil would block the information transfer. So he would, cover up the person. If he was treating the stomach, he put a little hole in the aluminum foil in here, and the laser would go right in there. So that at this point, that's pretty much all we know what would interfere. I think back to the previous question, interference and quantum decoherence is probably going on here, because if this is in fact quantum information that's being transferred, because quantum information doesn't stick around very long, it's not very stable, and all kinds of things in the environment could interfere with it, and perhaps even reverse the polarity of the information so that it goes produces an opposite biological effect. That is yet another explanation that the inhibitory activity is transferred to the laser, but by the time it ends up in the cell, it converts to a stimulatory activity. So those are two good points to consider, and thank you for the question.
I'll just interject here that I remember Dr. Omura-san having also the aluminum foil, and that he would charge the aluminum foil for healing energies, because I still have a little index. Oh yes, he's quite wonderful.
He's a character. I was going to say we might invite him here. Well, Dr. Omura did all kinds of unconventional things, and this was just one experiment that I did with him, and I thought, okay, wow, this is worth repeating, and in a more scientific way.
I just want to clarify my understanding of what you said, basically, and what I understood was a laser beam was passed nearby some material, and information was somehow picked up by the photons in this laser beam and transmitted to
the biological
system. Do you have any idea how that information was carried by the photons in the laser beam? Was it polarization that changed, or exactly what changed?
I think the laser carries the information in an analogous way to an electromagnetic field being modulated by frequency information.
What was the frequency information?
Well, that's what it's the frequency information is actually chemical information, which I described as originating from the electronic and the chemical bonds and all that stuff.
Mm-hmm.
That was I didn't have time to really talk about the mechanisms that the laser would carry the information, and I'm not even sure I even know, but I'd love to hear from some of the physicists in the group how a laser might, which is I guess your question, how the laser might carry the information. The information itself, I think, is the chemical information I described. Mm-hmm. How the laser carries it and how the biological system decodes it are two unknown questions at this point.
Thank you.
Thank you.
All right, let's give our last speaker a great round of applause.